So today I'm going to talk a little bit about how we put some actual numbers to what the building code requires us to consider when we're doing these designs to resist tsunami loads. So I'm going to switch over and start my slide presentation. And the first type of load I want to talk about is the forces due to very basic idea of buoyancy. The fact that our building may actually start floating in the as a wave surrounds it. So buoyancy is basically the idea that water is displaced and creates a force equal to the density of the water times the volume. So the first thing is the density of the water. The building code actually tells us to use a value of 64 pounds per cubic foot as the density of seawater, because the tsunami wave, of course, is expected to be coming from the ocean. But in addition, the code tells us we should increase that value by this coefficient K sub S, which the code tells us is equal to 1.1, and that's to account for all the debris that this water will pick up as it's rushing in from the ocean. That's the trees, the light poles, the dirt, the sand, broken buildings, boats, cars, anything that wave picks up and carries with it. So we're going to actually base our calculations on the idea that the fluid that we're floating in has a density of 70.4 pounds per cubic foot. So the code gives us this equation 6.9-1, which tells me that the upward force created due to buoyancy is going to be the volume of water we displace times the density of that fluid, which was that 70 pounds per cubic foot value. But there's also some rules we need to think about when we come up with the volume of the water being displaced. That's, of course, going to be the volume of the structural and non-structural components in this project. But we also need to think about the fact that there's going to be an airspace that may be trapped under the slab, especially if it's inside the beam soffits around the perimeter of the building. And there may also be some airspace above that slab, which is enclosed by whatever solid walls are being built above the floor slab. And of course, there's also the volume of the foundation, except we don't need to consider things such as deep piers or piles. Windows are going to have some unique requirements we need to talk about. Well, the first thing the code talks about is what's known as open versus closed walls. I've got this large wall in front of me. That wall may have windows, it may have no division between the interior and the exterior space. It may have what we call breakaway walls. Those windows, breakaway walls, they don't impede the water. The water is going to flow right through those. If I have less than 25% of this face of being solid portions of the structure, if I have less than 25% of this entire face that is solid structure, then I can consider this face being open, and literally whatever the water elevation is outside the building, I can expect the same elevation inside the building. Breakaway walls would have to be something that we've intentionally designed, that as soon as a little bit of water pressure shows up against the face of this wall, that wall is intended to break off and open up. Now, as far as windows, windows can be of different materials of glazing. Some windows are actually designed to be missile resistant, especially in hurricane locations where we don't want debris from a hurricane blowing through the window. The building may be covered with window glass, which is either designated as missile resistant or blast resistant. If that's the case, then I really need to consider those windows as being solid walls. We don't expect the water to be able to break them. Alternatively, if I don't have windows that fall into those two categories, then the code tells me that when the water reaches the top of the window, I can expect the window will have broken and the water will have flowed in. Alternatively, if I know how much water it takes to break the window, then I can use this elevation 2 as my upper limit. But I will say I don't know how many engineers are going to be very familiar with how much water it takes to actually break a window. So elevation 2 is going to have to be some information we can begin to collect with experience. So let's talk about what happens when water is coming in during a tsunami wave. I've got to cut away through a building exterior wall. There's a floor slab. There's this beam soffit underneath. There may very likely be a wall above the slab. Then on top of that wall is sitting some kind of a window. And then above that window, I've got the beam for the floor above. Now, my water begins to come in during a tsunami. It flows in through that window below me. The water rises a little bit higher, gets up to the beam soffit. But now, as the exterior of the water rises, no longer does water flow in underneath this beam because literally I've trapped some air, and that air won't allow the water to begin to fill this void. In fact, I'm going to keep going up here until I reach this elevation 1, the top of that window, at which time I'm actually displacing this full area above me, this full volume enclosed being from this elevation 1 all the way down to the bottom of my lower beam. Now, if I do know what kind of water will cause the window to break, then I might be capped off at this elevation 2. And of course, I never have to consider anything above the run-up elevation for the location I'm working at. If it turns out the run-up is much higher than the top of this window, I still don't need to consider this portion up here, because once it exceeds that elevation 1, then I expect the window to break and the interior space to begin to fill up with water. So let's work through a real simple little example. I'm going to say that I've got a building that is 40 feet by 30 feet. Its story heights are 10 feet. The dead load is 100 PSF and a live load of 125 PSF on each floor. Structure has a flat slab that sits on the ground and upturned concrete beams that are 4 feet tall. Windows continue from the top of the upturned beam all the way to the bottom of the slab on the roof. The run-up elevation is told that it's 17 feet above this ground level slab, and I'm being asked to determine the ultimate level forces using ASCE load combinations and the buoyancy effect of the tsunami wave. Well, the run-up was given as being 17 feet above the ground. That's far above the top of the building. So that run-up elevation isn't going to be an issue. If the water ever gets that high, the entire building is submerged. Now, I could consider this elevation 1 limitation if I knew how thick the slab was, if I knew the windows weren't missile resistant or blast resistant. But on the other hand, if I don't have that kind of information, it's probably best then to be conservative and to assume that the water could come all the way up to the level of the roof. So if that's the case, then my HSU, the buoyancy force, is going to be the load caused by the hydraulic effect of the tsunami water. That's going to be the volume of my building, 40 feet by 30 feet in plan, 10 feet tall, times this value of 1.1 times the 64 pounds per cubic foot, or 845 kips upward acting on my structure. I have a dead load, which is 40 by 30. I have two floors that both support 100 PSF. So I've got 240 kips total down. And for live load, I have a little bit more. I've got the same area, the 2 stories, 125 pounds per square foot, or 300 kips down. ASCE tells me I need to consider these two load combinations. So if I keep those numbers that I've calculated and I get rid of the forces that are not in this example, then my load combination 1 would be 90% of the dead load minus the upward force from the tsunami buoyancy gives me 629 kips upward. Considering load combination 2, now I consider the dead load plus the live load minus this upward force gives me a lower value of 407. The worst condition for buoyancy is going to be this 629 kips upward when I only have the dead load to help resist it. So in summary, buoyancy is the idea that water is surrounding this structure. It takes some time for water to get inside. So during that time, literally the building is trying to float in this fluid. The density of tsunami water is higher than fresh water. Code gives us some specific values for that. And of course, buoyancy force is the volume of the water displaced by the density of the water assumed. We need to consider the volume, the airspace under the slab when we come up with the volume. And the elevation of that water is either going to be this run-up elevation or the top of the window, or in some special conditions, we may have some different values to think about. Open structures are assumed to flood easily, so they're not going to create nearly the buoyant effect, but they require an exterior face to either be open windows, open spaces, or breakaway materials. So this is buoyancy. We're going to talk about some other types of forces that tsunamis create in the next several slide shows.